When people think about flying, they imagine cruising at 35,000 feet. Smooth air, stable engines, long stretches of calm. But for engineers and pilots, the most critical part of a flight happens far below that altitude. It happens in the final minutes. Landing is not dramatic because airplanes are unsafe. It is constrained because everything that can change has already changed. By the time an aircraft approaches the runway, almost every variable has been fixed. Speed, weight, weather, runway length, wind direction, braking performance. There is very little flexibility left. This is why landing is the most constrained phase of flight. To understand why landing is so constrained, we must begin with a simple truth. An aircraft is a system for managing energy. At cruise altitude, an airplane carries enormous kinetic and potential energy. But it also has space and time to manage that energy. Pilots can change altitude, adjust speed, reroute, delay decisions. During landing, that freedom disappears. Energy must be reduced rapidly, precisely, and within a fixed distance. Unlike cruise, where time is abundant, landing compresses energy management into seconds. This is the foundation of all landing constraints. As an aircraft descends, it enters what aviation engineers call a performance corridor. At the top of descent, this corridor is wide. At the runway threshold, it becomes extremely narrow. Speed must be within limits. Too fast, insufficient stopping distance. Too slow, loss of lift. Altitude must be precise. Too high, unstable approach. Too low, terrain risk. Alignment must be exact. Lateral alignment. Vertical glide path. Runway centerline. Every correction uses time and energy, both of which are running out. This narrowing corridor is not a flaw in aviation. It is a consequence of physics. Unlike airspace, runways do not move. A runway has a fixed length, a fixed width, a fixed surface condition. An aircraft must adapt itself to the runway, not the other way around. Landing performance calculations assume a specific touchdown point, a specific braking effectiveness, a specific wind component, a specific runway condition. These assumptions are conservative, but they are not infinite. If any one assumption shifts, even slightly, margins shrink. This is why runway characteristics dominate landing risk. Weather is not just an environmental factor. It is a constraint multiplier. Rain reduces friction. Snow reduces braking effectiveness. Standing water increases hydroplaning risk. Wind alters ground speed. A small tailwind may add hundreds of meters to required stopping distance. According to FAA and EASA performance models, wet or contaminated runways can double landing distance requirements under certain conditions. Nothing has failed. The design assumptions have simply changed. And during landing, there is very little room to adapt. By the time an aircraft descends below a few hundred feet, decisions become irreversible. Go-around decisions must be made early. After touchdown, stopping is the only option. Human factors research shows that decision-making under time pressure is one of the most constrained cognitive tasks. Pilots must monitor speed, monitor alignment, monitor descent rate, monitor automation, anticipate runway conditions, all while approaching the ground at high speed. This is why aviation relies heavily on stabilized approach criteria. Not because pilots are unreliable, but because human decision-making has limits. Modern aircraft are highly automated. Automation reduces workload, improves precision, enhances safety. But automation also creates expectations. Auto-throttle, flight directors, and landing systems assume correct configuration, correct inputs, correct environmental data. If automation behaves unexpectedly near the ground, there may not be time to diagnose and correct it. This is why aviation design emphasizes predictability over novelty. Landing systems are intentionally conservative, not because engineers lack confidence, but because they respect constraints. Aviation is one of the safest engineered systems ever created. And paradoxically, that safety exists because flexibility is limited during landing. Rules are strict. Approach angles, speed tolerances, touchdown zones, braking procedures. These rules exist because small deviations compound quickly. What appears rigid is actually protective. The system works not by allowing unlimited adaptation, but by preventing unsafe adaptation under pressure. Landing accidents rarely result from a single failure. They occur when constraints stack. For example, a wet runway, a slight tailwind, a heavier aircraft, a delayed decision. Each factor alone is manageable. Together, they push the system toward its limits. This is known as constraint convergence. The aircraft has not malfunctioned. The crew has not failed. The system has reached its boundary. Despite all these constraints, aviation remains extraordinarily safe. That is not accidental. It is because margins are defined, limits are respected, assumptions are conservative, failures are studied deeply. Every landing accident produces data. That data reshapes procedures, training, and design. This feedback loop is one of aviation's greatest strengths. Landing teaches us something fundamental about engineering. Safety does not come from eliminating constraints. It comes from understanding them. Engineers do not design aircraft to be perfect. They design them to operate predictably at the edge of limits. Landing is where those limits become visible. Not because the system is weak, but because it is honest. Landing is the most constrained phase of flight because time is limited. Energy must be dissipated. Space is fixed. Decisions are irreversible. And yet, millions of safe landings occur every year. Not because pilots are fearless, not because engineers are lucky, but because design limits are understood, respected, and continuously refined. This is not a story about danger. It is a story about discipline.